This is a tutorial for the AC Node Solutions tutorial in Circuit Tutor. I'm going to do a mastery level problem in hopes that this will address any bugs or complications you could run into in another level. So the first thing we're prompted to do is pick a ground node. I've arbitrarily selected this one. You can pick whichever suits your fancy. So as always, we start with our voltage constraint equations. I'm going to look at V1S first. On the left-hand side, we have V4. On the right, we have the ground. And that would mean that V4 minus 0 is just V4. And we can assign that to the value of V1S. Check the equation, and it works. So now we can do the same for V2S. On the positive side, we have V3. On the negative side, we have V1, which means that the difference of V3 and V1 should be given by the definition of V2S. And the definitions for these are found underneath the circuit diagram, in case you're wondering where these values are coming from. And it looks like there are no more voltage supplies, and the KCL equations are done for us. So we can move to the equations for control variables. And it looks like the control variable we have here is IX. Now you can see that IX is coming out of the J5 impedance, and it is moving in from the right-hand side and out of the left-hand side. So the circuit always moves in on the positive end and out on the negative end. So that would mean that IX is given by 0 minus V2, or negative V2 over J5. So that's why that one is minus. And then for our sought variables, we are seeking a branch current, and that equation is actually going to resemble a KCL equation. So you can see that there are three branches that enter the node V4. So we could say that I out is going to be coming into V4, which is negative, because we in KCL assume that positive current moves out. So that would be negative I out, negative 3IX, because IX is pointing into V4. We want it pointing out for positive. And then the current given by the negative J1 impedance would be V4 minus V3, because again, current is moving out, over negative Ji t equals 0. And that is an appropriate sought variable equation. And again, you can see the cursor reiterating the direction of those moves. So Circuit Tutor now is going to have us input all of these 5 equations. So the first 2 are fairly straightforward. We can see that V1 has a negative 1 and V3 has a 1 coefficient. And the solution to that is 5, 120. And then for the second equation, there's a 1 in front of the V4 and then a 4, 0. Now the third and fourth equations are a little more tricky, so I'm going to open up MATLAB for that. And you can see that voltage 1 of equation 3, and that's just the variable I use, but you can use whichever you prefer. And all I'm doing is putting the denominators into an inverse and then assigning that to that variable. And we can just copy and paste the answers into our matrix. And I've gone ahead and done that for all of the variables in the third equation and fast forwarded through that. So you can see the answers on screen there. But again, it was the same procedure. Now I'm moving on to the fourth equation. So V1 of equation 4 is given by negative and then the inverse of 6. And I again fast forwarded through all of the coefficients for the fourth equation, and you can see how to do them on screen. So now moving on to the fifth equation, you do have to do a little bit of algebra. All you have to do is shuffle one of the variables over to the other side, and you can again see the coefficients for that given below. So now we're going to check all of these, and it looks like we missed something. So V1 looks good, and looks like V3, we accidentally put 1 there, or we accidentally put a 3 there, so we change that. All right, it checks out. So now we are asked to put the equations that we just wrote into a matrix. And you had to scroll down for that. But all you have to do is just hit copy from the simplified equations and it'll put it in the matrix for you. It doesn't solve it, but it does notate it. So you don't have to manually re-enter all those values. Now, though, we do have to manually solve for all these values. And for that, I'm going to use MATLAB. So if you recall how to enter syntactically an equation, a matrix of equations, then this will go real fast. You can also see how I'm doing it on the screen right now. I've accelerated the speed because it's a little boring, but the gist of it is that you go from left to right, top to bottom, put a space in between each element, and then a semicolon when you're starting a new row. So you can see my mouse tracing the movement that you should be taking right now when you're entering the values. And you can also see in the command window how I'm entering those values. So we're now on the last row. Those are going to go in. And rather than ending on a semicolon, we're going to end on a bracket. And then I've actually chosen to suppress that because we don't need to print it out. We have more information to enter. So to create the matrix of the solutions, I prefer to do it all symbolically. So I'm just going to say that solution 3, 4, 5 are 0. Then for solution 1 and 2, we only have polar coordinates. But to enter those into MATLAB, we actually need Cartesian coordinates. So you can see that you can use the function pull to cart, and you have to assign it to a variable. You have to actually assign it to a point. So I've chosen x1, y1, and you can see that inside pull to cart, your first argument needs to be the degree, and it actually needs to be in radian form. So I put 120 times pi over 180, and then your second argument is the radius. So I'm just going to copy and paste that, and then replace the information with values appropriate for the second equation. So 0 degrees, radius of 4, and I'm going to assign it to y2 and x2 so that everything is stored properly. And then what we're going to do is say that solution 1 and 2 are equal to x1 plus y1 times I, because this is the form that MATLAB stores Cartesian coordinates. It stores it in the form a plus bi form. So now solution 1 and solution 2 are the Cartesian version of the polar coordinates that we see in Circuit Tutor. And then for our solution matrix, we can just go ahead and put in solution 1, 2, 3, 4, and 5. And then to find the answer to the systems of equations, we create a final matrix, which is equal to the inverse of the equation matrix times the solution. And this outputs everything in Cartesian form, but to input it into Circuit Tutor, we need to make it polar. So what we're going to do is we're going to say that x1, y1 is equal to the function Cartesian to polar, and then take the real and imaginary arguments from the first element in matrix final and assign that to x1 and y1. And you can see this in text where on screen I've copied it for all 4, v1, v2, v3, and v4. So now to print this out, all you have to do is remember that the radius is the y variables and the angle is the x variables. And you're going to have to take the angle and multiply it by 180 over pi to convert it to degrees. But then you can see for v1 how we've done this. So now we have output the radius and the degree measure for v1. And the arguments and the definitions that you see on screen are going to be carried out for v2, v3, and v4. So I'm going to fast forward through that and you'll see all the variables output. And they're all done now. And you can see in the workspace that we have quite a few variables, but they've all been put to good use. And then we're going to hit check answers. Looks like we did them correctly. So now we are asked to find the stop variable, which is I out. So all we have to do for that is when we make a calculation in MATLAB, we have to do it in Cartesian form. So for V2 and V3, you're going to call the Cartesian form, which is given in our final matrix. So final 2 and final 3. And then the rest of the equation will be input as appears in Circuit Tutor. I'm going to suppress it because I out is given in Cartesian form, which we don't want. We want it in polar form. And if you'll recall, the syntax for converting from Cartesian to polar is by cart to pole, and then the two arguments are the real and the imaginary components of I out, and we have to store that in a point. And then we just take that point and output the radius and the angle. So the radius is given by the y component, and the angle is given by the x component times 180 over pi, because we're converting it to degrees. And then we can just copy and paste the radius and the angle into Circuit Tutor. Check answer, it works, that's great. Now we have to convert this to the time domain. So this is a lot simpler. We don't need MATLAB for this yet. The radius in the frequency domain translates to the amplitude in the time domain. The degree in the frequency domain translates to the lead or the lag in the time domain. And then for the frequency term, recall that the time domain requires angular frequency. So, and that formula is given by angular frequency equals 2 pi frequency. So we've done 2 pi times 6 kilohertz in MATLAB, and then copy and paste that. And Circuit Tutor luckily takes exponent form. And then it says, this is all correct. Congratulations, you have finished the problem. And good luck in completing your